Okay, now moving on to the next presentation. This is coming from the pioneer of heterojunction, which is Huasun. We have Christian Combs, who is Director of Business Development Europe at Huasun. He's going to talk about meeting three goals of PV with heterojunction: high efficiency, high volume gigawatt scale production, and sustainability. Christian, the floor is yours.
Hello, namaskar. Let me share my screen. Now it works. Can you hear my screen well? Can you see my screen? Can you hear me well?
Yeah, both.
Perfect. So I will try to be brief. I always have problems with that. So I am sorry. I say already now. I want to take you first to overview of why we're doing what we're doing in heterojunction. If you look at the value of a module, maybe many of you have already seen a chart like what you see on the screen right now. You have something that is like an efficiency, but maybe as well the size of the module, how convenient it is for installation. You have the performance of the module that includes as well for long term, the reliability and durability. And you have the affordability of the module. This is very easy, is the contrary of the price. So depending on how you paint a module on this scala, you get the value of the module visually very easily. And you see if one module technology or one module brand is very unbalanced or balanced good for everything. If we go back in time to 2008, at the time I used to be at Sanyo doing heterojunction. Heterojunction was this dark object of desire for everybody who was doing PV systems, because it had higher efficiency than at the time poly cells modules, and it had much better yield, but the cost was very high. So at the end, it was kind of a niche product because the overall picture was very unbalanced. If we move forward to the future, everything looks so much better now with efficiency going up and the cost going down. However, what hasn't changed is that there is a gap in efficiency from heterojunction having, you mentioned this 15, 20 watt higher power for the same module size. And there is a gap as well in performance compared now, not to poly cells, but now compared to the darling of the moment, which is TOPCon. In terms of cost, it is still a situation where heterojunction is more expensive than this market standard, which is TOPCon now, but the gap has reduced. More importantly, everything has become better, but I want to talk about the gap. First, I want to put some numbers on the table for those improvements that we see and that difference between one technology and the other. Typically, if you look at modules that you can actually buy today, heterojunction, we are selling modules at 23% module efficiency. And if you buy TOPCon modules, you will be around 22%. So there is this gap. If we think about performance, the key numbers that we employ are the temperature losses, this is the temperature coefficient, and the bifaciality. These define how well one module will work on the field, what will be the specific yield. And in both metrics, heterojunction is a little bit better than TOPCon. Not only that, I want to point to these little numbers that I put in brackets. Even though you get today 0.26% temperature coefficient, for 2024, it is expected to improve. And the same applies to bifaciality, because the potential of heterojunction on those aspects is just higher than in TOPCon. And that will move into the next topic, which is what is the connection and implication of having higher efficiency or higher yield into the overall picture. And now I want to compare again what happened many years ago in 2008 to today. Back then, the module was very, very important in the total cost of the system. It was more than 50%. I remember sometimes being like 70% or even 75% of the cost. Right now, with a much, much, much lower module cost, we have a cost of the system that is dominated by the balance of system. And the implication for this is that any change in the performance and the efficiency of the module has a very large effect either on the cost of the system via higher efficiency or on the LCOE of the system with a higher yield of the module. This is because this now very small part of the system has a global impact that multiplies a lot its own price. So if you want to get, for instance, 5% more yield out of a system design that you did with a standard module, you can make a PV system that is 5% bigger. Or you can have a module that gives you 5% more energy. If you make a system 5% bigger, you multiply this cost by the system cost. If you get modules that give you 5% more yield, you only affect the cost of those modules. This is something that is quite relevant for utility scale, and we will go for that for the gigawatt production. Now I want to talk about some of the topics that were mentioned before by Christoph and giving maybe a more precise view on that. In this graphic, you have the most important innovations that have happened already in mass production in terms of efficiency and those that are prepared to be implemented. So we see that in the last couple of years, since 2020, a lot of things have happened. And the most important one probably is the inclusion of light conversion film. This is, as it was mentioned before, a layer in the encapsulant that will prevent ultraviolet light to arrive to the module, but not by filtering it off, but changing the light to a longer wavelength. I will talk about it later. Here in this graphic, I have put a nice star to those things, those innovations that are not only bringing higher efficiency, but they are as well bringing lower cost. And if you look at the overall picture, you will see that in the future, we have basically a lot of yellow stars that show that the innovations that are upcoming are going to be both increasing the efficiency and reducing the cost. This will come into play later. Obviously, everybody's darling in terms of the far future is perovskite, and we expect in 3 or 4 years to have mass production with a big jump in efficiency and a nice reduction in cost. This is the overall. If I go one by one, light conversion film, as I mentioned, is to change light from ultraviolet into visible light. Super multi-busbar is to improve the fingers and the bus bars on the cell to let more light in and reduce the use of silver. Microcrystalline silicon and nanocrystalline silicon are structures that are used on top of the intrinsic layers of amorphous silicon in order to improve the p-n junction. Zero busbar, I think we have heard so much about it, I don't need to say anything. And a thinner wafer and a heterojunction thinner wafer connects as well to what Christoph mentioned before, a better utilization of the ingot and then a reduction of the material cost. Indium-free TCO, here is probably, as Christoph as well mentioned before, one of the fields where more research is needed, but we already have some improvement that also increase the efficiency. And copper plating is something that we look into the future, maybe end of 2024, to become something on mass production. What is the reality of all of these numbers that were on the screen? The reality is that since 2021, we have been increasing steadily about 0.5% absolute efficiency every year in mass production. This number that you see here is what has come online in December from us into mass production with the wafers, rectangular wafers of 210 but rectangular. This is the reality and not some test or some record for efficiencies. In heterojunction, let me or allow me this small comment. It's quite easy to reach records that are not realistically used in real production. Because of two things. One, the cost of the production. You can do a record with some improved materials. And second, the reliability. You can do record with materials that will not withstand the pass of time. But if you go into mass production, you need to do things that are well done and cost effective. If we talk about these improvements, the one that, or the two that come to mind is one, the thinner wafer below 120 micrometers. And second, you see here that we use microcrystalline silicon, not for the first layers, the intrinsic ones, which are still or remain amorphous silicon for the passivation, but the ones that are built on top. And these become a construct of layers that are multiplying in number. The second point, and for me particularly the most important, is the implementation of light conversion film. This means in the encapsulant, we change light from this blue here, this is the incoming light, from the spectrum in the ultraviolet below 412 nanometer into, and the red is the outgoing light of this layer of encapsulation that is in the visible light, and more importantly, two things. The first one, that it doesn't damage the cell, it doesn't bring the hydrogen atoms of the hydrogen silicon chemical bond out of this chemical bond, and second, it brings the irradiance into a part of the absorption of the cell that has better quantum efficiency. The interesting part about this is not the slightly better quantum efficiency, is the fact that if you don't do light conversion film, you must do ultraviolet cutoff. This means the options are not to do this film or not to do this film, and to get a little bit more or efficiency or not, is to do this efficiency or to do a filter that will reduce the efficiency of your cell. Because if you don't implement any technology, you may have ultraviolet degradation. And this is, at least for us, not an option. Now I want to talk about gigawatt production. And the first point is that we do have gigawatt production, and we're not talking about 1 or 2 gigawatt, which for very large players who are in the 60, 70, 80 gigawatt total production is still a test line. We have 100% production of heteroaction, and this is, as of today, December 2023, 20 gigawatt in cells and in modules. We are vertically integrated. The second thing is the realization that when you do real gigawatt production, this has good things because they allow you to have a lower cost, and things that they push you to, it is that you cannot produce 20 gigawatt and stay selling high-price modules for rooftop applications, because the market itself will not be big enough for this 20, 30, 40 gigawatt production with the competition. This means that there is kind of a you use lower LCOE, or you must get lower LCOE. At the same time, you get lower cost of production because you have more production. The first point about the reliability is something that we take very, very seriously, and I have the satisfaction to say to any metric that you measure reliability with, heteroaction from us as of today is giving you equal or better performance than TOPCon. This is proven by long-term tests, but it is based on several aspects that have required optimization. The first one is the fact that the heteroaction cells with no laser scribing are fundamentally more flexible than TOPCon cells, and the mechanical load tests are just fantastic. So basically, if you have a heteroaction module, if the module is still intact and the glass is not broken, your cells will not have cracks. The second is, and it was mentioned as well briefly in the presentation before, that we do edge sealing in order to keep humidity out of the module so that the performance after 30 years of operation is still excellent. And the third one is the effect on reliability of this light conversion film that I already talked before. So What is the implication for mass production at gigawatt level? The implication is that we need to be at a price level in the affordability, because I talked about efficiency, I talked about performance, but the affordability must be good enough that the LCOE is comparable or better than with the established market leader. So is it there? I say it is there, very much so. If you look at the advantages because of the efficiency, you find that you have a lower installation cost, and this offsets some of possible high cost. If you have a higher performance, as we have demonstrated, you have an offset as well into the cost of the module. And right now you can buy heterojunction from main players like us at a price that is well within the range that you will offset with these two aspects. For the market introduction, I have to disagree with Christophe. He mentioned that he sees TOPCon as being the main player in the next years. I think it's because from the point of view of the just the outside of the industry, let's say, not producers, you are still focusing or keep your mind on the limited application phase. This is when the cost of a heterojunction system was so high that the LCOE in a normal application for utility scale was higher, clearly higher than TOPCon or monoPERC. And that only works really for very specific applications. There is a market, maybe rooftop, maybe some commercial industrial, but not very big. When you are, as end of 2023 is the case, where the offset in LCOE terms of the characteristics of heterojunction is already putting you as a competitive level, better in most cases than TOPCon, then you will see the rapid introduction of heterojunction as well in utility scale. And the same as TOPCon pushed out monoPERC of the utility market, we expect that heterojunction is going to enter this utility scale market in very huge volumes in the next 12 months. This is the mainstream situation. You are mainstream when even the EPCs who only care about the cost will buy your product, because you will be, or we will be, in next year in the point where the cost of heterojunction compared to TOPCon will be so similar that the total system cost will be lower with heterojunction. When we look at 2025, I think it is safe to say that it is really a situation where the cost of heterojunction should be lower per watt, only the module by itself, than TOPCon. And that is when we believe that the substitution of the technology on the market can occur. And this is the view, but the reality as well. We are not dreaming about something. We have a lot of gigawatt production ongoing, and this is going already to utility scale projects. There is this beautiful 400 megawatt project in Bulgaria, and that is a reality. This is a picture and not a rendering. This is almost all of it connected already to the grid. So this is something that the gigawatt production and implementation happens already. I want to finish with something nicer, which is CO2. And if you look at the CO2 emissions, or generally the sustainability of our industry, I want to mention that heterojunction, because it uses less silicon, because it does the production at a lower temperature level, and because we are using materials such as silver already at the similar level compared to TOPCon, we have overall already today, even without using silicon of, let's say, very low CO2 sources, we are already today below the CO2 emissions of the most CO2 friendly technology that is not heterojunction on crystalline silicon. Into the future, with the improvements that you saw in our technology roadmap, we plan to be well below 300 grams per watt. And this is something that we believe as well for the hundreds of gigawatts of production, and for the future laws that will be implemented everywhere in the world is quite important, and for the environment, of course. With this, I finish, and I don't know if there are questions. I think I was basically on time. So thank you very much.
Perfect. Thanks a lot, Christian. There's a very good analysis. So one question I have is, when you are saying that you will reach TOPCon in terms of LCOE. So what is the basis for the TOPCon? So how much is the efficiency delta, or the power delta you are keeping into account?
So let me give you some example numbers. So the efficiency delta right now is from 22 to 23%. In terms of watt, so that people understand, we are quoting right now with 720 watt, 715 watt in projects where the TOPCon that is quoting as well by official is at 690, 685 for 2024, middle of 2024. So this is the kind of delta in efficiency that will save you between 0.5 and 1 cent in the installation cost, depending on the system. If you have fixed tilt, it will save you less money. If you have trackers, it will save you more money. This kind of delta in the efficiency for the same size of module. In terms of performance, we see typically 2% higher yield for the same kilowatt peak. And if you do the very quick calculation that a utility scale system right now with trackers cost turnkey about 60 cents, 2% of 60 cents is 1.2%, 1.2 cents, and that is the offset that is created by higher yield. Just very clearly, because otherwise you need to build a bigger system where the system completely costs 1.2 cents more. So if you put one on one together, you see that as long as we are less than 2 cents more expensive than TOPCon, the customer today already has a lower LCOE. That is kind of the rough numbers. In applications like in the Gulf states or in India, the performance gap is much bigger. We see even 4% higher yield.
Okay. But on the other hand, it's heterojunction as a technology also growing, like what you have said, with this efficiency, performance increasing potentials. But the same things also exist for TOPCon, right? So have you also factored in that this can quickly close the gap, or you don't see that?
Yes. No. This is a fact. However, if you look at TOPCon and heterojunction, heterojunction has not had the amount of investment and R&D that TOPCon has had in the last 3-4 years. And the level of innovation in TOPCon is slower than on heterojunction right now, especially regarding innovations that bring both cost reduction and efficiency, which means that we see that 0.5% per year that has been achieved in the last 2-3 years is a much faster evolution than the evolution of TOPCon, which is, let's not forget, 50% of TOPCon is the monopair technology.
Great. Thanks a lot for this wonderful presentation. And if there are any questions, I already see 1 or 2 in the chat window. Please
I will answer in the
answer.
chat window.
Yeah.
Maybe let me, if I may, let me give a final thought or final thing that has been maybe a bit lost. Heterojunction, in one sense, we're standing in the shoulders of giants. I repeat this sentence a lot because Panasonic and Sanyo were almost 2 decades doing this. And this has a good thing and a bad thing. The good thing is that the reliability, contrary to some of the sentences before, is very good already from the start, because Sanyo Panasonic had to go through 10 years of problems before everything was kind of solved. But that happened already. So if you see modules and systems from them that were prior to 2007, they are okay. But if you see them after 2007, it's incredibly stable performance and customers know it. And that is kind of the strength of heterojunction. But Sanyo, basically Panasonic didn't invest anything in R&D, in real production R&D since 2009, 2010. So that time we can now very quickly improve in efficiency and in cost. And this is the super big chance of heterojunction.
Okay, so one question again on that. So, but Panasonic and Sanyo was also a very much pretty closed door. So how much of this technology or innovations, whatever they made, how much is being transferred to the rest of the world?
So let me put it this way: the innovations they did were under closed doors only to some extent.
Okay, thank you very much for this nice
My pleasure. Always
overview.
my pleasure.